for reasons that you learn in physics, and most people taking this particular course at this particular institution are taking physics simultaneously or have taken it. And if you have taken it, you understand that moment of inertia, the moment of inertia of a small mass about a given axis is just the product of the mass and the square of the distance from the axis. So that we would call that delta m times r squared. Now that's written kind of small, it's kind of written as an afterthought, but we add up all the mass increments delta m, each mass increment multiplied by the square of its distance from the axis. Well, then the moment of inertia of your delta rho by delta theta by delta phi increment with this density function, we're just continuing the same region with the same description and now the same density function. The moment of inertia of that region about the z-axis is the moment of inertia of the mass within your delta rho by delta theta by delta phi box, the box defined by those increments, okay, of rho, theta, and phi, where this increment is assumed to contain the sample point rho star, theta star, phi star. The mass of the material inside that box is 1 plus rho star cosine of phi star times rho star squared sine phi star d rho d theta d phi. And then you have to multiply that by the distance from the z-axis. This is your mass increment. This is your delta m. Okay, the density times the volume is the mass. And this is the distance from the z-axis. That's the distance of the point rho star, theta star, phi star from the z-axis. And of course, we're squaring that because that's what you do to get moments of inertia. From physics, you should understand why. So here is the contribution of this delta rho by delta theta by delta phi box containing rho star, theta star, phi star to the mass, and multiplying that by the distance of this box from the z-axis. You're multiplying then the mass by the square of that distance, and that's your contribution to the moment of inertia. And moment of inertia is usually designated by I, so we'll call that just delta I equals this. Now you sum these up over all rhos, all thetas, and all phis. Well, that just gives you an integral that just looks like this one. And the only difference in this integral and the integral you get here, well, this integral came from just the mass, because this was the integral for the mass. Okay, and we see how this much of the expression gave us this quantity here. And you see that all we have to do to get the moment of inertia is add the rho sine phi, so we multiply by rho sine phi. So you'll have an integral of rho sine phi times 1 plus rho cosine theta, etc. I don't have room to write that out, but that's it. So the same limits on the integral, the same volume increment, rho squared sine phi d rho d theta d phi, with the density function, give you the mass. If you then multiply that by the square of the distance of your typical point from the z-axis, you get the moment of inertia. And let me just comment, it should be clear why rho sine phi is the distance of the point rho theta phi from the z-axis. Within this plane, same as any other plane, but within this plane we're seeing rho clearly, we're seeing phi clearly, and we see this triangle here that has hypotenuse rho and angle phi here. The distance from the z-axis is just this distance, and that's the side opposite the angle, where the hypotenuse is rho, so this distance is rho sine phi. Now, I really shouldn't have to point that out to you, but yeah, I probably should. I probably should point it out. You need to get used to that. These things need to be second nature. If they aren't, you simply need to keep working problems until they are. Now, we haven't actually done the integration, but the integration is straightforward. It's no more difficult than the integrals you did in your first year calculus. And I'm not going to take the time to do a lot of those integrals. I do have a lot of videos, the alternative videos on your website, where I work through a lot of details for a lot of integrals. Here, I just want to focus on what things mean and how we set them up. So that's an example in spherical coordinates of how we set up a mass integral, a volume integral, a mass integral, a moment of inertia integral.